Alright, number 11. You guys notice, technically number 11, well in the Jamboard right now, if you're there, if you were to go back one slide, there would be an example of problems that we did not do on Thursday because I was like, well, it'll show up in homework, I'm sure you guys will ask a question if you need it, and we'll go over it, etc. And you did. So, here's number 11. Just checking real fast, guys, at the beginning of number 11 question, did they ask you to make an augmented matrix, yes or no? Was that 11A?
Yeah. 11A was just... Yeah.
Did they call it an augmented or did they call it a doubly augmented? What did they say? Just augmented, right?
I believe so.
Okay, so if they wanted you to do an augmented matrix, hopefully you guys would have done, let's see, 1, 1, negative 3, 4, negative 1, 2. Now, as I am making this question, what would the directions in part B?
To solve using the
Gauss-Jordan elimination, right? Okay. So, something that I do believe should have been here somewhere. Although I think it would have happened in 8.1, not in section 8.2. So let me write it off to the side. If I was talking about Gauss-Jordan elimination, what does this correspond to? Gauss-Jordan elimination. Do you guys remember?
Row echelon.
Not REF. That was Gaussian elimination. Careful. Gauss-Jordan is one step further. And what's the REF one step further?
Reduced.
Exactly. So what is it telling me to do to this matrix?
Solve for the zeros.
Solve for the zeros and the ones. Well, technically, where are we supposed to start with?
Getting the ones.
Getting the ones, but I already have the one. Go, team! So we're going to get zeros. And how are we going to get zeros?
By multiplying the second row.
Multiplying the row with the 1 by the opposite, which in this case would be a positive 1, in this case would be a negative 1, and then we have to add to wherever we're trying to get our 0, right?
Yes.
And so we would end up with this guy staying the same as far as 1, 1, negative 3, 4. Then we would have, we're just adding, I think, because 1 plus negative 1 is just 0, so 1 plus 2 is 3, negative 3 plus 0 is negative 3, 4 plus negative 4, got him. But now I need to subtract, or no, what did I do? I did a negative and then plus. So a negative 1 plus 1, a negative 1 minus 1, a positive 3 plus 1, a negative 4 plus 7. Once we get some zeros and a column is good, where do we move? Over to the next column, right? Kind of like we do with matrix multiplication. We go to the next one. And to go to the next one, what do we need to get right here along the main diagonal?
1.
Do you like how I'm bringing that vocab in? Main diagonal? You guys all go in the right direction? Right? Yes. Main diagonal, don't we have to, wait a minute, how do we get ones? Zeros we add and eliminate. How do we get ones?
Divide.
Exactly, but specifically multiply by the reciprocal. So everybody else is going to stay the exact same as far as 1, 1, negative 3, and then 4. First row is good. Last row is good, at least for now. 0 times the reciprocal is still 0. I'm maintaining that first column, but then divide by or multiply by 1/3, multiply by 1/3, multiply by 1/3. Gorgeous. Once I have my 1, what do I do?
Find 0.
Find the zeros above and below. Find the zeros where I need to continue the column or finish off the column. Multiplying this guy, who is now row what?
2.
The 1 is in row 2. By the opposite of whatever I need to eliminate. So either a negative 1 or a positive 2. So negative 1, row 2 plus row 1. Some of you I heard last week, you're like, man, that RREF thing, you keep on changing it. It's like, well, but the system is the same. I know the numbers keep changing, or the rows I'm using keep changing, but the system remains the same. Okay, as I get in here, second one stays the same now, right? Second row. So I have 0, I have 1, I have negative 1, I have 0. Boop, 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 boop. There we go. And I do what? Negative 0 plus 1 is just still 1. Negative 1 plus 1 is 0. Negative 1 minus 3 is negative 2. And negative, well, 0 plus anything is still itself. 2 times 0 is 0 plus 0. Got it. 2 times 1 is, minus 2 is 2 times -1, -2 plus 4. And then 2 times 0 plus, well, 0 plus anything is itself. And once I have the second column done, where am I headed?
Reducing the three.
Down to the third column, the end of that main diagonal. Trying to get that guy reduced, sure. But trying to get that guy to be a 1, so I'm going to multiply by the reciprocal of 1/2. Man, we're just reviewing like all of chapter 8 right now, right? Isn't this kind of 8.1? As we go over 8.2, as we get ready to go into 8.3. 1/2 of 0, 1/2 of 0, 1/2 of 2, 1/2 of 3. Bleh. Oh well. P.S. These are going to stay the same. P.S. These are going to stay the same as long as you follow your system. Oh, these are all staying the same. I'm not even changing them yet, but I'm about to change them because how do I finish off my column?
Get the above zero.
Get the above zeros, which makes it RREF. All you do is eliminate those. So to eliminate those, the opposite of what's there times the guy with the established 1 added to the row that needs it. The opposite of what's there times the established 1 row added to the guy that needs it. He is good. So I already know that Z is equal to 3/2. Or x3 is equal to 3/2. I'm trying to find x2. And I'm trying to find x1. Those of you guys that are making mistakes, have you found it yet? At this point, all I should need to do is go ahead and finish off my matrix. Question?
So if, in like the one where the 1 is circled in the third row, you, like, say like the one above it was like a 3, then would you multiply it by, like,
It meaning row 3?
yeah,
Yeah.
like if row 2, if you were like trying to get that
Had a
zero,
positive 3. Mm-hmm.
okay, then you'd add a positive 3, but then
No, if it was a positive 3, I'd be multiplying the bottom guy by a negative 3.
Okay.
Does that make sense?
And then once you change that to a 0, the third row stays the same as it was before.
Yes, because he's good as is. He has his 0, 0, 1. Does that make sense? Okay. Any other questions? Are we good? Yeah.
So you said reduce row echelon form. What is the name for that again? Something Jordan?
Gauss-Jordan. Gauss is in the mathematician, G-A-U-S-S.
And that,
Or you could say Gaussian is like Gauss made into an adjective.
because I got confused when doing it, because I thought it meant, because there was something similar, like a name.
Yeah, if it was just Gauss, or they would call it Gaussian elimination,
Gaussian.
then it would be REF.
So Gaussian elimination is
Just here and here, Gauss-Jordan says finish it off.
Okay.
Yeah.
Thank you.
Like that collaboration got it all the way. And you guys can check with your graphing calculator and make sure that you have it at that point, but I think we're good to go. So, we're on to number 12, aka the word problem, aka the last problem, aka the one that we thought was 13. Okay, so, an electronics manufacturer produces 3 models of LCD TVs which are shipped to 2 warehouses. The shipment levels are represented by A. What's in warehouse 1, what's in warehouse 2, and how many of each different model? The prices per unit are represented by B. Wait. So, I mean, if we were to label things, because this one's labeled, this one's not. If we were to label, wouldn't this just be like price, right? But what would be up here? Why are there
1x,
3?
2x.
No, specifically looking here. What would label each of these columns? But which ones?
Price
Televisions?
Which ones?
LCD. From warehouse 1.
What models?
LCD.
LCD.
3 types of LCD.
Read the matrix.
Oh yeah, the three. The
Named
three
what?
different
Oh,
types.
Oh, there we go. Okay. Does that make sense?
3 models.
So why are they multiplying B times A?
Find the prices.
And it's only with a multiple.
Yes.
Could I multiply A times B?
No.
No, it doesn't make sense. But what does make sense? I don't have anything split up by warehouses, right? Remember, matrix multiplication, you go across as you go down. I don't have any sets, people say it different ways. But I don't have any of those sets organized by warehouse. So I have nothing to multiply because I have nothing else organized by warehouse. But what do I have prices organized by? Models. What do I have my warehouses broken down into? Models. Can I multiply a 1 by 3 times a 2 by 3?
Yes.
Although, hold on. How do we do order again?
Row, then column.
Oh, so what would I be multiplying it by?
3 by 3.
Okay, so that was a mistake on order, not a mistake on, oh, can I now multiply them, yes or no?
Yes.
Because as long as those match, right, I'm good to go.
Yes.
Now they are going to ask us for like a interpretation in just a second, but if I was to multiply them, it would be completely legal. So for instance, I could go ahead and say, I don't know, I guess I could make that an X and make that a Y and make that a Z just for sake of not worrying about the numbers. If I was to multiply, I would go ahead and have $4,000 times like the price for that model. Let's see, we would go across and down. So I'd have this times 4,000 plus that times 6,000 plus, I'd go cross down. I'm doing it in the wrong order, 7,000 Z. So that would be the first, right? The first row times the first column, but then I would also need to do the first row times the second column. I do cross over down, like we just talked about, like how we had to go over to the next column. So then I would have, no, not 4,000. Now I'd have 2,000 plus 12,000 plus 5,000. Now, when you guys did this in your calculator, what people did that? I mean, hopefully there are decimals. Couldn't you put in both of these matrices and multiply them B times A, right? Hit enter and then you get your whole multiplication. True?
Yes.
But does looking at it this way make a little more sense for what's actually going on? Because they ask you for an interpretation, I think, after you solve it with your calculator. Question. What is this product? What is this multiplication showing us? What will these two numbers represent?
How much money each warehouse is making from
Good.
the models?
It's going to be how much money. And what'd you say, Joey?
The
In each what?
warehouse.
Exactly. It's all about, do you know what the labels are? This is warehouse 1. Everything that's in warehouse 1, how much that's worth as far as what they could get out of it, and how much in warehouse 2, how much it's worth, how much they could get out of it. So if one of those warehouses burned down, and they wanted to know the value of the merchandise, they'd be like, well, this is what we could have gotten out of it, right? Or if warehouse 2 burned down, or if warehouse 3, or if you wanted to think about like where the crime rate is higher, and should we really have this much amount of merchandise like this? Yeah, this much merchandise. I mean, it's specifically talking about the price and about the money involved for that merchandise. But yeah. How does that line up to the different options that they gave you? Well, they gave you, oh, where's what was it? I don't know. It's on the, it's on the Pi Day song one. The number of LCDs, definitely not. You multiply it by money. The cost of the 3 models at the 2 warehouses, I don't love how they worded that, but yeah, that technically works. Because just warehouse 2, no, you multiply by both. Just warehouse 1, nope, you multiply by both. And the number of units, definitely not. It has to do with the cost. All right, and then you end up throwing in, you're like, oh my goodness, it's worth a lot of money when you guys put it in your calculator, right? Quick questions, quick questions. Has to do with money. The only word in there that had to do with money was cost. And so it's the cost of all the TVs combined at, and then here's where it got separated, each warehouse. Is how I would maybe try to put it. And they put it somewhat similarly. Ryan, recording, go ahead.
So all those systems can equal the prices and be like the first equations can equal like $649.
Oh, it's not going to equal, we're multiplying. So remember we do cross down, so this times this times this, this times this. I just named them so I wouldn't have to write all the messy numbers. but it's gonna end up being an amount of money, an amount of money, an amount of money. So those 4,000 TVs could bring in how much? Those 6,000 TVs are worth how much? To them, those 7,000 TVs are worth how much? Let's add it all up and we figure out how much they're worth.
So it's the row times the first column.
Cross down, yeah. So thinking of multiplication and cross down. When we say cross, we're thinking row. When we say down, we're thinking column. And then like from last time, remember? They're not written next to each other. So I go across and down, and I add them all up like a dot product. And then I cross over and down, so I have the exact same thing at the second warehouse. And I thought it might let you see a little bit easier about how we took every single model times its corresponding price and added it all up. That's what the matrix multiplication did for us.
Yeah, it's just like I got the first one right, but the second one I don't resolve. So maybe I just.
Oh, it could have just been inputting it wrong. Especially if you're just throwing this in your calculator because we have these nasty decimals with word problems. If you were doing it by hand,
Yeah, it's about
it could have been very easy just to type one of the prices wrong. Especially if you got the first one right, you had the process done. Yeah, you definitely had the process done. Okay, any other questions on 11 or 12, section 8.2, due tonight by, am I giving you grace? Is it 11:59? Ah, spoiled rotten. Oh.
Thank you very much. Even I think.
But still, you like that you had the option.
Yes.
Here we go. 8.3, how did inverses go? 8.3, how did inverses go? Just the idea of inverse, nothing to do with the matrix yet, just the idea of inverse. P.S. You are going to want your graphing calculator out and ready to go. You want your notes out and ready to go. But in the very, very beginning, we were just trying to remember the idea of an inverse. And guys, what is the idea of an inverse?
undo.
Undo button. Hey, we've learned something. Anybody else thinking undo?
No.
Nice. 2 people. Well, we're trying. Okay.
Homework and pen.
Undo. Wait, this is new. This is new. This is new. Let's go. Paul, Joy, Baron, computers put away. Let's go. Unless it's the Jamboard. And if it's the Jamboard, just make sure you're writing notes. You're not doing homework. Here we go. Notes, not homework. Here we go. All right. For number 1, cool kids, how do we solve for x? Add 2 to everything?
The first one?
Mm-hmm.
I said ln. First you add 2, then you
First we add 2, and then why is Ryan saying ln? Ah, because it's e, and what does ln of e? What is that relationship? They are, oh, they cancel, aka they are inverses because they each other. So therefore, I end up with, now hold on, how am I able to say this is an easy problem to solve? Where'd the ln go?
Because always the one.
ln of 1 is always 0 because 1 is where the logarithm goes through the axis, because anything to the 0 power equals 1. There's this whole back and forth thing. But anyway, yeah, that's a memorizing thing that most people take a long time to memorize. So therefore, what's my x? Ooh, that was close. Okay, how about number 2?
Good question.
divided by 2. Divide by 2.
Divide by 2. No, don't distribute. Cosine. Cosine has this a plus b, a minus b. Cosine, sine. I don't think we want to do that. So cosine, sine, cosine x, cosine pi. Cosine, the signs change, plus sine x, sine pi. That would take a long time. It might be easier just to go ahead and say, let's keep the cosine as it is. It's not cosine times, it's cosine what? Of. Woo-hoo. We did learn multiple things. How do we get rid of a cosine?
Cosine inverse.
Cosine inverse. And cosine inverse should have me thinking backwards, unit circle backwards. Is there ever a place that cosine is 1/2? 1, 2, 3, 3, 2, 1. Ha! Pi over 3. Anybody get there faster than me?
Then you add
Remember, multiple ways of thinking about it. One way is your cheater chart. In cheater chart, it goes so, then ka, then toa. 1, 2, 3, 3, 2, 1. Hey, 1/2 is right here at pi over 3. Ta-da! The other way is cosine is the adjacent. The adjacent is this one. Which one is the little, not the medium, not the large, but the little one? That's pi over 3. like there's some sort of math. But as we get here, question. What leads you to x is equal to 4 pi over 3? I know it's silly, but it's actually important for calculus. What math leads you from here to here? Plus, but question, how did I get the plus pi to be 4 pi over 3?
When you're adding it, you have to multiply the pi by 3 to add it.
I can multiply by 3 over 3. I hear Ryan and Paul both talking about it. It's a 3 over 3, and what's a 3 over 3 plus a 1 over 3?
4.
We're learning fractions in pre-calculus. Don't worry, you'll learn them in calculus also. Is that the only one? Probably not. Is that the principal one? Yes. What was involved in both?
Miss, inverse.
Inverse and undoing. Go ahead.
Is the cosine inverse of 1/2, is that pi over 3?
Yes.
Okay.
And I drew two different things over to the side. Sorry, they're kind of in and amongst the Pi Day and homework questions. But one was the cheater chart. That's so ka is 1/2 of pi over 3. Or that the adjacent side is the little one. Not root 2 over 2, not root 3 over 2, but 1/2 happens at pi over 3. Couple different ways of visualizing it. But question, what chapter are we in? It's not exponentials and logs, and it's not trig. What is it?
A matrix.
Mm-hmm.
It's not asking for the number.
It's matrices. So, does anybody know any of the terminology up here? What do you think the capital A is representing?
Some kind of complex.
The opposite of a lowercase f.
Well, A could be an angle in geometry. A could be a point, a vertex of a triangle. A could be a capital article beginning of a sentence. But guys, what is A in chapter 8?
Algorithm.
What is no? What must capital A be talking about, especially if they're giving you the hint that it's an n by n? Yeah, exactly. It's a matrix. Capital letters represent matrices. A, B, C, D, etc. So A is a matrix. Hey, when I see it's an n by n, what does that mean about the number of rows and the number of columns?
Unknown. Oh, yeah, that's just the column.
Unknown, but they are the what?
Columns and rows.
The N's, or the M's and the N's.
Because it's an n and an n and not an m and an n, what do I know about the size?
Columns times
The dimensions are the same, and therefore we can call it a square matrix. Hey, is there an important matrix that has an I in it?
Inverse.
No, well, maybe.
Diagonal one.
But actually, I was something we talked about in section 8.2. He's a very, very special one that can go in any order because what does he do?
Identity.
Aha! He maintains the identity.
Identity matrix.
That's why we had to be careful though, because inverse starts with I, right? So I is identity, and identity, remember, he's the one that has a main diagonal of what? Ones, and everything else is...
zeros.
Does that make sense?
Yeah.
That's just a period.
Just keeps going. Technically in every direction if you want to think about it. As long as it's square. Oh my goodness. Do I have all the directions yet? I think so. Okay. The identity matrix. The leading diagonal, main diagonal of ones. Everything else zeros. So what do you notice about the matrix definition of an inverse? First of all, who is the inverse? If it's not I, what represents inverse up here?
A negative one.
Aha! Because we've learned in the past an inverse like f negative 1, but we would never call it that because that makes you think reciprocal when really it's f inverse. But we've seen this notation before, right guys?
Yes.
Okay. And what do you notice about what's happening with the multiplication of a matrix and its inverse?
It's equally the identity matrix.
An identity matrix is the most basic, simplified. Hold on. What did ln and e turn into?
1.
It turned into 1 times 3x plus 1. What did cosine inverse of cosine turn into? 1. Multiplicative identity, multiplicative identity, multiplicative identity. Muy interesante. Beep. The question, what if they just want us to see that these two are inverses of each other? We can look at them and say, interesting numbers, yay. But how can we show that they are inverses? Because right now, a B isn't necessarily related to an A. So what do you guys think? What did the definition say had to happen for these two to be inverses?
They would
Ah.
A and its inverse will have to equal the identity.
So if we multiply A times B and if we multiply B times A, what has to happen?
They both equal the
Reduce
identity.
So let's test it and see. And if either one of these fails, either we did bad math or they're not inverses of each other. Hey guys, with matrix multiplication, does A times B always equal B times A?
No. Unless it's squares.
Oh, wait.
Well, a square can be multiplied because a 2 by 2, a 3 by 3, like they're gonna work both ways. Ryan's thinking like if you change the dimensions and switch it, it's not always legal.
Oh yeah.
But just because it can be multiplied, does that mean it's gonna equal the same thing? Not necessarily. They're only gonna equal the same thing if they go down to the identity. So okay, let's see. We have to cross down, right?
Yes.
Yes.
A times B, I'm going across these guys and down those guys. Are we good?
Yes.
Okay, remember what happens when I point to things? What do?
Same amount. So what they equal.
-1 times 1.
Multiply, good. So what's -1 times 1? -1 plus 2, right? -1 plus 2. Cross down, cross over, down. 2
Plus.
plus -2.
So 0.
Hold on, if you're not watching, you're not getting the practice. It's so easy once you get it, but you gotta practice it to get it. So we did -1. Remember, whatever we point to, we multiply. -1 plus 2. +2 minus 2. Or plus a -2. But that was just for the first row, first column, first row, second column. For the first row, first column, first row, second column entries. What do I have to do now?
For second row, second column.
Because if we were looking at these, it's a 2 by 2 and a 2 by 2, which is legal, but I should end in a 2 by 2, right? Okay, second row, first column, -1 plus 1. And then
2.
2 minus 1.
what do we end up getting? 1, 0, 0, 1. Hey, how'd that go?
Easy.
It's a two-dimensional identity matrix. It's a 2 by 2. All identities are square. We don't have to say 2 by 2. We can just say I2. BA. What's going to change that time?
Wait, so Misty, we're
Yeah.
trying to figure out if B times A and A times B equal the same thing?
Equal the same thing and are the identity, but to equal the same thing, that really only happens if it's an identity. Well, I guess, unless they were the same thing, like 2, 2, 2, 2, 2, 2, 2, 2, I guess that would equal the same thing also. So I can't say only identity, usually identity, Andy.
Okie dokie.
You guys cool if I show that this time we're doing this guy across and this guy down?
Yes.
Right? Everything just switched? Going across him as I go down him, right? B comes first and then A, so he's the cross and he's the down. So, watch the pointers. You multiply what I point to, right? For the first row, first column entry, I need the first row and the first column. Cool, what's that? -1. Hold on. There we go.
Plus 2.
Plus 2. Okay, for the first row, second column entry, I need the first row, second column. Cool. Multiply. 2 minus 2. Or 2 plus a -2. For the second row, first column, I need the second row, first column.
Plus 1.
Got it. And then for the second row, second column, I need the second row, second column, 2 minus 1, or 2 plus a -1. How's it going? 1, 0, 0, 1. However, we don't just want to stop with the, oh, that's what an inverse is. Or, oh, that's what an inverse does with matrices. Instead, we also want to know, but how do we find it ourselves? If inverses are so helpful because they take away what's in the way, or they're able to undo what's been done, if inverses are so important, we need to have a way of finding them ourselves. So, cool kids, look for a pattern. Do you see anything that's similar, or the same, or almost the same between A and A inverse?
All the numbers are the same, but on B it's just -2, -1 instead of on A it's
The sign
-1,
flips.
Interesting. So like it's a 1 and 2, like the magnitudes, the 1, the 2, the 1, the 1, the 1, the 2, the 1, the 1. Yeah, they're all the same.
But the negatives are just
Except for what?
Everything is
negative.
it's like the positive in a negative.
Everything's opposite.
Yes.
So that's a that, and that's a that, and that's a that, and that's a that. Huh. I wonder if that's what always happens. Couple key vocab. That page was not to teach you how, it was just to see if you could find a pattern. And so far we figured out, well, all the numbers seem to stay the same, but all the signs just switch. That's not a big deal, is it? Okay. Few definitions. First of all, that guy that we just saw, A, he was what we call invertible. He was what we call invertible. Why? Well, because he could be inverted. There you go. Because he had an inverse. His inverse exists. But if the inverse has to be able to multiply both directions for AB, has to equal the identity of whatever size I have, has to equal BA. This is only possible with square matrices. So question, will any non-square matrices ever be invertible? Nope. So if B is A inverse, then AB times BA, both equal to the identity. It's only possible to multiply both directions if I have a square matrix. So therefore, I can say all non-square matrices are singular, aka non-invertible. But we don't say that for matrices. We say singular instead. You can think forever alone. That works too. Forever alone, they don't have an inverse. That's not saying that relationships and spouses are inverse. That could be tricky. Anyway, coming back. But, silly way of remembering it. They're single. They're alone. Poor little guys. But a better way of thinking about it is specifically, they cannot be undone. Oh, that's an interesting. Once again, no life lessons are happening. Non-square matrices cannot have an inverse, aka cannot be undone. Which is interesting. Having to do with a couple applications that are coming. Singular, single, don't have an inverse, can't be undone. I mean, that's maybe a kind of cool thing, kind of powerful thing, but also kind of a tricky thing. Because in math, we like to be able to do and undo. Ryan.
So for the last, the problem you did earlier with B times A, how did you multiply it again? Because I know how to do A times B. But when you do it the opposite, how do you do it again?
Most people, in order to do it the opposite way, their brains would work a lot better if they just rewrote it to make the B go first, then have the A go next, because your brain has gotten into like this pattern of multiplying.
Oh yeah.
And it looks nicer this way. But as you get really used to it, you can kind of just say I'm going across and going down and be able to make it work, which I did, but you saw me slow down, right? I definitely went way slower when I was going the other direction. So it's usually easier to take the time, and then you can see like, oh, and it gets you.
And so because they're the same thing, that represents other inverses.
Well, that's a big question mark in our heads, because I asked, do you guys see any patterns? And the patterns they saw, all the numbers the same, all the signs opposite, and in your heads right now, some of you are like, I think that's all it takes. I haven't said yes or no, which is a bad sign, as to whether or not it always works like that. All we know for right now is multiplying got us an identity, and multiplying got us an identity, so we know it's an inverse only by seeing it and trying it.
Okay.
So far, that's all we know. And we have some vocab. Woohoo! Vocab. Vocab's gonna be up there for 5 more seconds in case you want a quick picture of it. 5, 4, 3, 2. You guys all get the vocab, okay? Vocab invertible or non-singular versus singular. Singular, those are the ones that don't have matrices, which include all non-square, but also maybe some other ones as well. Here is one way to solve for the inverse. Here is one way to solve for the inverse. If the inverse is the matrix, that would fill in the multiplication spot and make the identity. If we wanted to be really, really, really detailed, we could say, okay, cool, then we can just say, who are you, and make you, okay, we could make you all kinds of different x's, which would could go on forever to whatever size you might need, but since it's small enough, I'm going to go ahead and simplify it a little bit and be like, hey, it's A and B and C and D. And I could do little things like, I know how to multiply. Cross. Down. Do you? I hope so. And we could do things like, 1A plus 4C. Or 1B plus 4D. Or negative 1A minus 3C. Or negative 1B minus 3D. I could do some multiplication, and with that multiplication, I'm like, hey, if I need that to be the undoing of this, then I can say, guess what? You have to make that. And you have to make that. And you have to make this. And you, what are we talking about in the back? Have to make this. Does anybody see chapter 7 screaming off the page? Systems of equations.
Elimination.
But wait. Does anybody see? We're combining. We're not grouping like terms, but kind of. We're like seeing what has to be true. Do you see any things with A's and C's?
Yes,
Like,
they are all
hey, A plus 4C has to equal 1, and negative A minus 3C has to equal 0. So couldn't I do a little like, woohoo, C has to equal 1?
Yes.
I know, part of my inverse. Back substitution, I can plug that in, and then I could say A has to equal negative 3 after doing a little back substitution and subtraction. And then couldn't I make another system for who am I missing?
B.
Oh, B's and D's, and they have their own thing, because B plus 4D has to make 0. Negative B minus 3D has to make 1. Oh, elimination. Boop! Man, I'm really glad we have like 1s and negative 1s in this one. Other ones might take more work, but D is equal to positive 1. Quick little back substitution and subtraction, B is equal to negative 4.
You make 2 separate systems.
Well, I'm just grouping to do what I can, right? I could make one huge system, but then I'm like, well, those two will be helpful, and these two will be helpful. So wait, this is a new problem, right, with new numbers? Let's test your guys' hypothesis. An inverse is the exact same numbers, different signs. All right, let's check it. Who would A inverse be if this did the job? Looking for this guy. I think we just found him. A is negative 3. B is negative 4. C is 1. D is 1. What was your guys' hypothesis last time? Everything stays the same and in the same places, even though you didn't say it. Everything stays the same and in the same places, just the signs switch. Okay, that didn't work. But there is a pattern, I think Brendan's saying it. There is a pattern that is the same. So what you saw wasn't what was actually happening. What you saw wasn't exactly what was happening. What is happening? What do you see, Brendan? What switched?
The negative, like everything is still times negative 1.
Everything? I think he stays himself.
Or like the same
And he
places,
stays
same
himself.
spots.
Which things did change signs?
4 and one of the ones.
Let's go see if we can figure it out from over here then. Switched.
Oh, it could be opposite.
Matrices tend to work with diagonals. Could I say that this switched and this switched?
Yes.
And could I say that this switched and that switched? Mm-hmm. But what did the main diagonal do? It didn't switch signs. It actually swapped places. It actually didn't switch signs. It swapped places. Does that work?
So the one diagonal switch are multiplied by negatives and then the other switch sides.
So then, okay, what if... Oh, we could check with multiplication. Blah, 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 blah. We already did that once. What if... Well, before this guy, can I pull... Oh, that's a boring one. That's a boring one. That's a boring one. Where's an exciting one? That's a boring one. Do you guys only have 2x2s this entire section? Oh.
I love
Okay. What if I was to give you a more interesting one? I just want you to ponder it. If you don't want to write it, you don't have to write it, but ponder this one. Ponder. Ponder A is equal to... Okay. How fun would this be to solve the exact same way we just solved the other one?
Oh wait.
No, it's not.
1, 2, 3, 4.
You just said
A, B, C, D, E, and
Oh, this one's a bit more.
count backwards.
Because we would need to have it make a three-dimensional identity matrix, so a 3x3. Guys, how many equations are we going to have if we're going to have a 3x3 identity matrix? This one we had 1, 2, 3, 4 because we had a 2x2.
Oh, 6.
9.
Oh.
Do you remember section 7.3 and how section 7.3 was the RREF section?
Yes.
Actually, it was you have 3 equations, 3 unknowns, and we pair them, and we pair them, and we go for that pair, and then we get z equals, and we work our way back.
Wrote that shit.
It was before matrices. So, question, how much fun does it sound like having 3 different systems of 3 different
That
equations?
is so
Torture.
fun.
Does this way work? Yes. But could the systems get really messy really fast?
Yes, absolutely.
I just went up 1 degree. I just went up from a 2x2 to a 3x3, and the work got exponentially worse. So let's talk about another way to kind of simplify what we just did. Instead of saying A, B, C, D, and like multiplying and then making a system of equations, which, no thank you. Here's another way of doing it. Another way of doing it, new vocab word, but not really. I'm not augmenting just with one column, I'm augmenting with a whole other matrix. Ooh. Doubly augmenting is taking like coefficients, but not setting them equal to like just a column. But putting them together, augmenting with a whole other matrix, what I want it to become. And what do you guys see on the other side about what I can do to find the inverse? The RREF is just going to take a little bit, well, I don't know about longer, because all I have to still get is this guy to be the identity. But the idea is, as I do RREF, isn't RREF breaking a matrix down to become an identity? And as I perform RREF to the entire thing, what you end up doing is breaking down A to become the identity. Undoing the one. Anybody ready for like every superhero villain story ever? You break down the one, you undo the one, and as you undo the one, what do you build up? The other. The breaking down of one is the building up of the other. By doing RREF, you are completely undoing the A, and as you undo the A, and as you perform the row operations all the way across, as you break down the one, you build up the other. As you break down the one, you build up the other. As you build up the one, you break down the other. Anyway, kind of works both ways. And if for any reason this does not work, well then it's not invertible. Now, you guys know how to do this as far as your actual row operations. You would just be doing it all the way across. Let's go peek at our calculator real fast, because we could take something like that one that I just showed you. And we could go ahead and see, like, okay, well, how could the calculator do it using this idea of a doubly augmented matrix? All right, hopefully you guys know how to make matrices by now. We doing okay?
Yes.
We're going to make a 3 by 3 because it was like, yeah, we're not doing A, B, C, D, E, F, G, H, I. No, we're done. Who is it? 1, 2, 3, 3, 2, 1, 2, 1, 3. Okay. But wait a minute. I want to doubly augment it. So do I just want it to be a 3 by 3? Or do I actually want it to be a, instead of just a 2 by 2, wouldn't this be a 2 by 4? So what would the 3 by 3 be? Not really a 3 by 3, but a 3 by, Because I don't just want the matrix, I also need to have it lined up with 1, 0, 0, 0, 1, 0, 0, 0, 1. Nice thing is it's really easy to put in that identity matrix, right? Oh, that was not in the right spot. No, it is. It just went over. You guys see what I did? I put in my matrix. I augmented it, aka I extended my matrix, I brought in the identity, I put the two together. The appropriate identity would be a 3 by 3. And now what do I need to do to the whole shabam?
Second matrix. And then A.
Or do you guys just do alpha A? That works. No, wrong one! Oh, sad day. I must have hit the wrong one. It's B. B. I want RREF. Of, second, matrix. If it's invertible, it will break down the one and build up the other. Did it work?
Yes.
How can you tell?
Because it's the same thing as yours.
The, as mine. Oh, yes. But why is that the inverse? Because what happened to A? It was completely reduced down to the identity matrix. You guys remember alpha y equals number 4 says nasty decimals. Don't worry, we got you. Oh, hey, look, that's nice. But what happened to our nifty little pattern of flip the mean and make the opposite the opposite? switch the main and multiply the opposite by the negatives. Did that work in this case? What do you guys think? Do they just switch these numbers and make those the opposite numbers? I see fractions. Like, where did the fractions even come from, right? Where did the fractions even come from? P.S. You guys know there's another way to do this? I wonder if you guys can find the calculator button. P.S. It's not hidden in a hidden menu. It's actually there in plain sight, but they've programmed it to mean different things in different cases. Interesting. But even though our little shortcut, which seems kind of cool for 2x2s, might not seem to work for 3x3s, well, it doesn't mean that it's completely pointless to have this shortcut. I think I'm going to go ahead and... No, I can show this one.
When it's a 3x3, would we just use our calculator?
Probably, right? Probably. But just to model for you that double augmenting, if you actually have to do it by hand, and just to kind of have it written down someplace, we take a matrix, we doubly augment it with its corresponding identity matrix. Hey, wait a minute, what if the matrix isn't square? What identity matrix do I use then?
Singular.
What if the matrix isn't square? What if it's a 2x3? What identity do I use then? I thought the identities were only square.
Can you look at like an inverse of something?
Look back at the word singular. Aren't all non-square matrices singular, aka they can't have inverses because they're not squares? So why would you even be doing this to a non-square matrix? Good catch, Ryan. If I wanted to go ahead and do this, anybody see I'd be multiplying the first one by 1/4? Michelle, I'm coming to you. But are we okay with me multiplying the first one by 1/4?
Yes.
How come? And didn't we already do something like this earlier today because you guys had me review row reduced echelon forming things? Right? Okay, Michelle.
I was just gonna ask what about
Yeah, make sure phone on desk, sign up, okay? Thanks, kid. Just leave your pencil back there. And then once I have my beep, 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 I established 1. How do I get my 0? Come on, solidify it. You guys got this. Good. Not by -1. By 3. Because I need, wait. I need to get rid of the 3. So I'm going up to that. Where is the 1? Multiplying row 1 times the 3, adding to row 2. Are we still getting there?
Yes.
I'm going to keep this one, -1/4, 1/4, 0. Keeping that. 3 times 1 minus 3. Gorgeous. 3 times -1/4 plus 1. How am I doing that math in my head? How am I doing that math in my head? What did I do last week? What did I do last week? I can make any number into a common denominator just by multiplying by the top and bottom, right? So if I knew I was going to have that, let's just think of that as 4/4, and then 3 times -1/4, -3/4 plus 4/4, 1/4. Gorgeous. 3 times 1/4 plus 0, I mean, that's kind of basic. And 3 times 0 plus 1, oh, I didn't even need that. How do I progress to the second column? Make that into a, by multiplying by the reciprocal, 4/1. Will always work. I know it's 4, but I'm just, following that reciprocal idea. 4/1 times 0, 4/1 times 1/4, 4/1 times 3/4. Nice, 4/1 times, cool. And all I need to do is get rid of that -1/4, and I can do that by multiplying by the opposite and adding. So multiplying by the opposite, not 4, 1/4, I need the opposite, and then adding, right? One-fourth times 0 plus 1, 1/4 times 1 minus 1/4, 1/4 times 3 is 3/4 plus 1/4 is 4/4, which is 1. And 1/4 times 4 is 1. And I end up with my A inverse to be what was built up on the other side as the other was being broken down. 1, 1, 3, 4. Which seems to also, right, follow my pattern of switch those two and then opposite these ones. Opposite, check, switch, check. So this is a pattern, like it is a thing. It just doesn't really work for anything bigger than 2x2s. It doesn't work. But 2x2s, there definitely is a pattern there. So let's go ahead and talk about that pattern. That's basically where we're going to end today. But go ahead, Ryan. What's up?
So how can you tell if, I know that anything, any matrix that's not a square is singular, and that means that this is not inverse, right? How can you tell if the matrix is squared?
Is squared or is
Is
inverse?
squared.
Is squared is just its dimensions. So it's 2 down and 2 over, so literally it's like the shape of the square because the rows and the columns are the same. We would call this a 2x2. And the fact that those dimensions are the same. If you go to the store and if you get a 2x2 piece of wood, it's going to be a square, or maybe it's going to be like a cube. But it's still going to be like square because of the dimensions, but a 2x4 will be rectangular because of the dimensions.
So since the dimensions are the same, that means it's squared. So if they're not, that means it can't have it.
Right.
Okay.
Right. So any 2x3, 3x4, 4x2, any of those will not ever have an inverse.
Yeah, that makes sense.
Yeah. So here's that nifty pattern that you guys didn't even realize was there. Well, you realize parts of it, but not all of it. So if you guys notice, as we finish off for today, finish off does not mean you're already done. Finish off means we persevere to be done. Because we're almost there. In a race, this is where it's getting the hardest. You're so close. You gotta finish well. Unless there's switchbacks. But anyway. This pattern, the whole swap sum, and then switch the signs of the other. It's swap and switch, switch and swap. The main diagonal is a swap. The opposite diagonal is a switch. Swap the terms. D goes to A and A goes to D. Make opposite the other terms. B becomes a negative B. C becomes a negative. You should see that right here as far as they are swapped and these are switched. However, do you notice that there was something else hidden that you might have not even realized all along? Who the heck is this guy? First of all, this guy has a name, and his name is right above. This guy has a name. And his name is right above, and he's also actually the same thing as section 8.4. So we're going to talk about him a whole lot more. Remember that dot product guy?
Yes.
Now he's like, he's important. We'll learn how to do him, but he could be used in tons of ways. That's kind of like this guy. We're going to learn how to find him. Just as a heads up, that he could be used in lots of different ways.
Did I say 2 times 2? 2, not 2.
2 by 2, like a 2 by 2 matrix. Sorry, it's a little baby. 2 by 2. However, unlike the dot product, this isn't a plus. What is this guy?
A minus.
A minus. But maybe that minus helps me remember that some things are opposites. Oh, the BC is in that's a way of remembering. But AD, I multiply the main and I subtract the opposite. So you can think it's the product of the main minus the opposite. That's also another way of remembering the pattern up here, because you can think, swap the main, and then make opposite the opposite. That's another way of remembering it. Swap the main, make opposite the opposite. But here is a really, really, really cool trick at the very bottom. Ryan was asking me just a second ago. He was like, how do you know if it's not invertible? Like, who are those non-square things? And we figured out the difference between square and non-square, but there's a problem. Even the square ones might not be invertible. And the really cool thing before we do all kinds of work to know whether or not there's an answer, oh, we like that because we like the no solution ones. We like the impossible ones. Right? Some of us always waste a guess on hoping that it is an impossible one. Anyway, coming back. This is the invertible test. It all has to do with the determinant and whether the determinant is non-zero. If the determinant is non-zero, it has an inverse. If the determinant is 0, it does not. The invertible test, the determinant cannot be 0. David Tan, what's up, bud?
Oh,
You good?
Yeah.
Noah, what's up? Yes. Pencil in the back, phone at the desk, sign up. Thanks, bud. So the ironic thing is, all the way up until this point, it was like, wait, the pattern works. Wait, well, not for him. Okay, but the pattern works. Wait, the pattern works. So who's the determinant guy? Like, we didn't need that. All we needed was this. Well, let's check out these guys. If we were just to do the pattern, if we were to just do the pattern, the pattern says switch or swap the main and make opposite the opposite. Similar over here. The pattern, if it was just the pattern says swap the main, make opposite the opposite. But the question is this what your calculators would give you? Now let me go ahead and show you a quick shortcut on your calculators, okay? Because I said there was one. Curious if anybody could find it. Said it means different things in different situations. Let's check it out. First of all, I have two different matrices. One of them being, I'll go put it in as you guys are writing them down. Let's see, we have a 2 by 2 of 3, -1. I don't need another negative. Struggle bus. I just need to use this. -1, -2, 2, and then B. We can name more than one. He's already a 2 by 2. -3, -1, -6, 2. Okay. Ready? Let's check our answers and see, was the pattern enough? Go get your matrix A, or I'm going to go get my matrix A. With my matrix A, what button looks like an inverse?
Oh.
What? No, I thought that was the reciprocal button. Like, what is 1/3 reciprocated? 1/3 reciprocated is 3. It is the reciprocal button, but they programmed it to act like the inverse button of your calculator. That's kind of snazzy. You don't even have to go to another menu. But question, was my pattern Because I said it was 2 and 1 and 2 and 3. Hold on. This, I think, would work if we just had a 4 and a 4 and a 4 and a 4. Hold on. Let's check. Is it 1/2, 1/4, 1/2, 3/4? So then the question is, where on earth did the 1/4 come from? And here's where the 1/4 came from. What is AD minus BC for this one? If you were to check and see if it even had an inverse before you went and did work, what is A times D? Well, guys, what is the main diagonal? What are those numbers?
1.
The main diagonal is not 1.
3 and 2.
Ooh, that's scary. The main diagonal is 3 and 2. What's the opposite? Remember, I said main minus opposite.
2 and...
-2 and -1.
So question, what's 6 take away 4? No, 6 take away 2?
4.
Is this invertible? Yes. Why? Because it's not 0. But do I have one of those guys? The answer is yes. So the inverse would come from 1 over times my pattern of 2 and 3 and 1 and 2. But wait a minute. Why didn't we have to think about this before? Question. What was your, before we learned it, your AD minus BC of this guy? What's 4 times 1?
4.
Minus, what's -1 times -3?
3.
What's 4 minus 3? 1. Did I have an inverse? Yes, I had an inverse because it wasn't 0. But question, did I see the pattern be different? No, because it would have been 1 over 1. It was fine. But wait a minute, what about this guy? Because you had 3 of these that the pattern worked for. And I said, I know, but what do you think was the determinant of every single one? A times D minus B times C is going to end up equaling... What's a -3 minus a -4? Did the pattern work? Yes. I only needed it, but there was a 1 over 1. So every single one where it was just the pattern, it was just a special case where the determinant was 1. So to be able to do any inverse, now careful, this only works for what size matrix? Not even any square, but a 2 by 2. So it's great for a 2 by 2, but what did I have you doing for a 3 by 3? Graphing calculator. Oh, hey, wait a minute. I had you check the whole doubly augmented thing, but what did we just say the calculator could do? Oh, we could just do the inverse button, and then it just takes us straight to the answer. That could be a cool shortcut for a 3 by 3. But the 2 by 2 does have a nifty shortcut, and the shortcut is always start by asking yourself, is it possible? This actually works for bigger ones too, just the formula changes. But asking if it's possible, we just say, okay, what is the mean? 2 times 3. Minus, what is the opposite? Multiply together. Up.
0.
Oh.
It's not possible.
Oh, so what can we say if it's not possible?
No solution. No singular.
Nice. Can I say non-invertible, and then you guys know that means no inverse, right? Whoop. Okie dokes. So then what's left? We could practice. We could practice. That'd be in the calculator. What's wrong? Because 2 times 3 minus 6 times 1 would be 0, and if I plug it into my formula, 1 over 0 just stops me. No inverse cannot be undone forever alone. Okay, so I think this will be our last one, because then we could just, you guys already figured that out, because I told you how to do the inverse in a calculator, and then we're done. So let's just stop here with one application of an inverse. To solve for a variable, guys, wouldn't you have to like do inverse operations to move things to the other side, right? So then the idea is, can I do that with a whole system of equations? Can I bring all of my coefficients? The answer is yes, by the way. I'm just kind of showing it to you. But the question was, Can I bring all of my coefficients? Can I pull them away from all of my variables? By the way, this is what really happens every time we do our REF to our matrices. I'm taking my coefficients, I'm kind of factoring them away from my variables, cross down that with that, cross down that with that, setting it equal to 2.4 and negative 8.8. And if I set this guy equal to A, how do I use A inverse to solve? I just say, well, what does A inverse do to A? What's going to happen if I found A inverse on my calculator, for instance, or with my formula? What happens if I multiply this times A?
Identity.
I would get the identity. This guy would still be here. But guys, algebraically, do I ever just multiply something on one side?
No.
What I do to one side, I have to do to the
Other side.
Now, with matrices, is order important?
Absolutely.
Yes.
Absolutely. So I could not go multiplying this on the other side, or all kinds of bad, impossible error codes could come up on your calculator. But if I was to find the inverse, I could actually just multiply that inverse by these solutions on the other side, and I would have my final answer. If I found my inverse, I would have the identity of my variables would be equal to that final multiplication. Okay. And with that, we are done with what we're covering today as far as 8.3.
Wood. Pine.
Engineers.
Scale.
Influential.
And anything to do with the circle, and anything to do with.
I don't really like percents.
Why would they want a Greek letter for 2 pi instead of 1 pi? Why on earth would you want 1 letter for 2 pi? Because 1 tau would be 1 circle, half tau would be half a circle, 1/4 of a tau would be 1/4 of a circle. There'd be no calzoning. On your guys' Google Classroom, you do have a link to USA Today's article on Pi Day because it has some pretty snazzy 7-Eleven down the street. What? McDonald's? Also Taco Bell, Chuck E. Cheese, Domino's, Papa John's, Papa Murphy's, BJ's, other places. But what else do we have?
My friend Tara, video game journalist, mathematician,
Pie enthusiast.
Pi enthusiast, because it's Pi Day. It's March 14th, so we're at Mission Pi. You're not supposed to be celebrating Pi, you're supposed to be celebrating the
Free calendars.
So we figured 2 for 1.
McDonald's free apple pie if you make a $1 purchase on their app.
Explain first of all,
On their app.
to anybody who doesn't know, so Pi, 3.14, what is the significance here? What does Pi define?
The actual number pi is really nothing special. It's an irrational number, so it's infinite. There's, an infinite number of digits, and it's seemingly random, which is not all that uncommon because most numbers are irrational. The significance of pi comes in the fact that it's a constant that's used in almost every area of science. It's used in math, it's used in physics, it's used in astronomy, and it explains a lot of the things about the way our world works that we don't necessarily understand.
So on a basic level, Pi describes the ratio between the circumference of a circle and the diameter, right?
Yeah.
Okay. So then how does it get this larger significance of explaining the world around us?
That's a good question. Nobody really knows what the actual significance of it is. There's no way to calculate a circle without knowing pi.
So Pi is endless. How long have we been trying to calculate Pi?
I think the first sort of proof that somebody had a concept of what it meant were the Babylonians. People have also said that the ancient Egyptians used pi in their construction of the pyramids. That's still sort of up in the air.
In the Bible, God kind of talks about it with the construction of the tabernacle, PS, but it's an approximation.
Are definitely some coincidences there. You take the length of one of the sides of the pyramids and you double that, and if you divide that by the height, you get pi. People have sort of given it like spiritual or religious implications. I don't know, I guess it's sort of open to interpretation, but people do love finding patterns in numbers.
They do, like you hear like Albert Einstein's birthday is March 14th,
Yeah.
pi. And then you hear 360 degrees in a circle, and if you go 359 digits into pi, the next digits are 360.
Yeah, that's sort of a stretch, I think.
Yeah.
But there are definitely coincidences. The way computers calculate it now is basically just by doing a series of fractions. And actually, the first person who rigorously approximated the value of it was Archimedes, and he used the polygon method, which is basically taking a circle, putting a hexagon inside that circle, so all of the points touch the circle, and then putting another one outside, so the circle lies tangential to all of the hexagon sides. What you have when you do that is an upper bound and a lower bound for what pi is, and if you do that, adding one side to the polygon every time, you basically get a close enough approximation. Yeah, that window closes and
It
you
eventually
get.
becomes a circle.
Yeah,
Mathematically, that's called converging. And just to end off, I think there might be one bad word, so forgive me.
And I found pi to be very useful because you can ask someone what is pi, and by their answer you can tell what field or what work, kind of job they have, because everybody has a different answer. Like if you ask a mathematician what is pi, they'll say it's the ratio of the circumference of the circle to the diameter, because they won't be pinned down to a number. Damn mathematicians. You ask a physicist what is pi, they'll say 3.14159, and if they're committed, they'll go on forever. You go away, come back, 6.72349, you go away, come back, 12, 19, 12. What the hell was that? 12. It's a drunk physicist. 12, 27. But if you ask an engineer what is pi, they'll say, yeah, about 3. But I would use 4 to be safe. And you didn't hear it from me. I'll deny it if you ask. You should look it up. That was a guess, man. I have no idea. I don't want to crash anything. I'm not responding. I gotta go.
And if you guys want, last but not least, oh, where is it? Oh, it's here somewhere. No, it's not. If you want a game to play just to celebrate Pi Day, whoa. I'll let you guys figure out what it is. What do you guys have that popped up on your Google Classroom today? A Zoom notification. Before that, what assignment popped up on your Google Classroom? If you want it, grab it now. It's only going to be up there for about 5, 4, 3, 2, 1. Well, it's a bonus assignment. It's not that big a deal. Pi Day celebration. Here's the version that you were supposed to get. On the article below, you guys have some different ways to celebrate pie. Some of the best ways are eating pie or pie-themed food, aka circular or semicircular, or someone brought up the idea of tacos at Taco Bell. As long as they're hard shell, they technically could celebrate too. By jogging or walking 3.14 miles, somebody asked, can I make 31 kills on Fortnite? I mean, I guess you're celebrating. I don't even know. That was a 9th grader. For bonus homework, plus 5 points, attach a selfie or screenshot of you celebrating Pi Day in one of the 3 ways listed above, or some other creative way. Participating in the Senior Pi Day, Pie Ice Cream, Pie Face fundraiser. P.S. Slices of pie available today at lunch will be blueberry, homemade cherry, homemade sweet potato, kind of like pumpkin pie. What else? Apple pie, that's the Costco kind, the really good kind. And it's going to be $2 per pie slice, $2 per ice cream scoop, or why? $3 for an a la mode? In honor of Pi Day, and maybe engineers, I don't know, it's okay, keep going. Pi Day potluck, I know, that was what was supposed to pop up, and then it didn't, so I have a small contribution. Sky's the limit. Okay, however you celebrate is up to you. When would be the best time to celebrate this? Today, a lot of the deals expire today. What deals? Yeah, like a $3.14 BJ's pizza, or I think it's a single pizza though. Or $3.14 7-Eleven pizza, or free apple pie at McDonald's if you make a $1 purchase, but something about the app, read the article. Taco Bell, free coffee, not really sure what's going on there, it's a little bit weird.
Domino's has $3.
Windows has something, Domino's has something. What else? Papa John's has something, Papa Murphy's has something, anyway. Happy Pi Day! Celebrate, screenshot but you have until the end of the week in case I didn't give you time. Alright, cool kids, if you want to ski, take one for the national week.
I'm like committed, bro. That's great. I keep forgetting where they are. There's gonna be like 7 many of them.
We should probably go into this so I think so far, like,
No, oh my gosh. Let's go.
actually, I built it. Your sister. Is there anyone else?
I'm gonna ask
Yeah.
the group outside.
Ooh. I bet somebody flips out.
Hey, John.
Natalie, no. There's no water. I still have. It's like the credit.
Sarah, ready for the soup?
Oh, give me no. Oh my god.
Oh, I lost it.
Oh.
He's ready. He's
What are you guys doing? We're doing extra.
The QR code's on the board.
Oh, come on. Can I just run 3 miles?
Party pooper.
That's literally one of the options.
Never miss.
Alexis, I was so sad. I posted an old version.
Never miss.
An old what? An old version of the assignment. The new version had a potluck with it.
No, you're not. Yeah, I am.
It did the old version. It's okay.
I'm dead!
I brought cookies. I know. I typed it out and then it didn't save it. Huh.
Oh my god!
It made me like pose with the board.
I can't believe we're in the video. Oh, 160!